All right, so the second part here on transformations are the horizontal ones. Just like everything we've done all year, the horizontal ones are weird in comparison to the vertical ones. Vertical ones, normal, they go the normal direction you would expect. Horizontal ones tend to be kind of goofy. Okay, so we're using sine as our background for this one. So this one is a shift of sine. Just like the last example that we did, if the number is added or subtracted outside of the parentheses, it moves it up and down. A number added or subtracted in the parentheses moves you left and right. And the thing to remember is the sign is always opposite. So x minus pi over 2 is actually going to move you right by pi over 2. Yeah, okay, that's decent, I guess. So you'll notice, like in this table, none of the y's are going to change. So I kept all of the same y values. It's the x's that are shifting over. Okay, so if I shift everything over to the right by pi over 2, that should make sense because now our starting point, like if I want to get a 0 in here in the parentheses, I should plug in pi over 2. Because if I plug in pi over 2, that'll be 0. Then I'll get sine of 0, which is 0. So the starting point of my table is actually pi over 2. Okay, so that is my new starting point. And I apologize that the writing of this is not going to be great, but I don't want to take forever writing it. So pi over 2 actually turned out pretty good. Good, so that means we are now starting here on the graph, which, if you look at it, here was the original starting point, moved 2 boxes to the right, essentially. Okay, and once you realize that, everything else is just going to move along with it. Okay, so everything on this graph is going to move right by 2 places. And so, if you want to use the graph instead first with horizontal stuff, sometimes that's actually a lot easier to do. So, like this point here, pi over 2, 1, I'm going to move it right 2 places, okay, which is going to land at pi. It's going to be at pi 1. So like it was here, I move it right 2 places, it's going to be there. So my next point is pi 1. The third point, pi 0, if I move it right by pi over 2, it's going to end up at 3 pi over 2. Okay, so it was here. If I move it right 2 places, it's going to end up there. Oh boy, 3 pi over 2, huh? So 3 pi, that's pi, dang it, over 2. Not the best. Okay, so that's 3 pi over 2. Okay. And then the point that was on the bottom here, 3 pi over 2 negative 1. Move it right 2 places. It's going to be at 2 pi now. So move it right 2 places. We're now at 2 pi. Okay, so it's 2 pi negative 1. Okay, unfortunately, the next point is going to be off the graph. But this is a good chance to just sort of get a feel for how this counting is working. Because you notice you're getting all the same numbers, in the top of this one, as you got in this one. They're all just shifted over. Okay, and if you haven't noticed yet, like how they count, like the gaps between them, all we're doing is moving 90 degrees each time, and 90 degrees is a half a pi. So notice it was 0, 1/2 pi, 2 halves, 3 halves, 4 halves. 2 pi is just 4 pi over 2. So 0, 1/2, 2 halves, 3 halves, 4 halves. The next one in that pattern then is 5 halves, or 5 pi over 2. Okay, so that'd be over here and back to where we started. And so there is sine shifted over to the right by pi over 2. Now to fill in the rest of the graph, which you should do because it gets you again comfortable with that pattern, just follow it. So it's bouncing back and forth between -1 and +1. So we just came from 1 back to 0, down to -1, back to 0 to +1. Just making that sort of zigzag pattern go through. So there, up, down, and coming back up. Okay. So that is a shift of right pi over 2 to sine. And you should be able to do the same thing with cosine. Just moving those x's. Maybe you move the graph first, or maybe use the graph to help you move the table. Again, these are all four interconnected: the equation, the transformation, the table, the graph. So any one should be able to lead to any of the others. Okay, so that's our first shift. All right, so looking at example 2, when we did the vertical ones, we did stretches and compressions. Okay, a number multiplied on the front of an equation is going to stretch it out vertically. A number multiplied on the x is going to have horizontal stretches and compressions. And the way I think about this, and these are super common because they're actually the thing that makes a wave not look like this slow rolling wave, but actually speeds it up so you get that quick, like sound wave sort of vibe to it, is by putting something on the x. Okay, so in this case, we have sine of 4x. So this is our basic graph again. Sine of 4x, the way that I think about what's going on there is I think of the number on the front or the number in there as being like the speed it's going. Okay, so sine of 4x, if I'm writing myself a little note about that, I'm thinking of that as moving 4 times faster. Okay, so these waves are really going to get rolling because to go through all the angles, if I put a 4 in front of the x, it's going to take way less x's, or it's going to take way smaller x's to make that full 360 degrees or that full 2 pi. So sine of 4x is going to speed it up to move 4 times faster. Okay, what does that actually do to the x's? Well, if I'm moving 4 times faster, what that's going to do is it's going to divide. I'm going to run out of room here. Divide the x's. No, let's go back. Please go back. Okay. It's going to divide the x's by 4. So divide x by, divide x by 4. Nope, still not going to work. So 4 times faster. It's going to divide all the x's by 4. I can't type it in there without making a mess of everything. So just going to leave it alone. Okay. So if I take this first x and I divide it by 4, I still have 0. I didn't change where it's starting. Okay, it's still starting at 0, 0. Okay. If I divide pi over 2 by 4, okay, so if I take this and I divide it by 4, all it's going to do is make the denominator of each of these fractions bigger, 4 times bigger. So if I take half of something and I divide it by 4, I'm going to get an eighth. Okay, so magically, we now have pi over 8 for that value, because 4 times faster is going to take 1/4 as much time. So when it did take pi over 2 before, it's going to take 1/4 of that. Okay, the next one, if I take pi and I make it 4 times faster, if I take a pi and I cut it into fourths, I should have pi over 4 for my next point. Okay, my next point over that, if I take 3 pi over 2 and I divide that by 4, that bottom, again, will become an 8. So I'll have 3 pi over 8 right there. And then if I take 2 pi, this ending point, and I make it 4 times faster, so I cut it in 4, 2 pi divided by 4 should just be pi over 2. Like if you have 2 pi's, you cut them in 4 equal parts, you've got a half a pi a person. And so there we go. So if and when I graph these, it's going to move 4 times faster. So let me take out the pen and do that. So 0, 0. Pi over 8, 1. Well, we have pi over 4. Pi over 8 is half of that, so half of that, 1. Okay, pi over 4 is 0. 3 pi over 8 is halfway between pi over 4 and pi over 2. So I'll be right there. And then pi over 2, 0. Okay, so again, this kind of work, it's really good for trig stuff, but it's also really good for fractions and spacing and stuff like that. Like now we're counting by eighths. So notice we normally count by halves, but if we go 4 times faster, now we'll count by eighths, because eighths are 1/4 of halves. So 1/8, 2/8, 3/8, 4/8, and so on. Okay, and so if I try to draw this decently at all, I'm going to have this sine wave that now is moving way faster. Okay, originally it took 2 pi to make one full loop. This is the first thing we've done that's affected the period. Okay, so period again is how long it takes to make one wave, basically. Well, now it only took pi over 2 to make this one wave. So the period of this, if you want to make yourself a little side note, the period of this is now pi over 2. It is 1/4 what it used to be. Okay, and then from there, you just follow the pattern. 1, 0, -1. Keep the same spacing that you just did. This one could get annoying to do, but you just keep it rolling as long as you can. And so you'll notice, oops, notice I'm really terrible at drawing fast. But you'll also notice how many waves did I get in here, or how many cycles did I get in where I normally would get 1? Well, I got 1, 2, 3, 4. Okay, and that's where that 4 comes in. I get 4 times as many waves in the same amount of space. Okay, and I could go the other direction as well. So back down, up, down, and so on. And I'll let you just take and connect those dots yourself, because that's just a pain in the butt with the mouse. So yeah, so we can speed up a wave pretty easily just by putting a number in front of the x. Okay, so that's our second transformation. All right, and now for our last transformation and our last example. It's similar to the one we just did because we're still working with the speed of it. So before we had, well, we have cosine now, we had sine before, so it changed the original function. But before we had a 4 in front of the x, which made it go 4 times faster. So if I put a 2 under the x, if I divide by 2 instead of multiply by 4, well, we're going the opposite direction. So if I wanted to speed it up, I multiply it by something, so it go 4 times faster. If I want to slow it down, I divide it by something. Okay, so this one, there's multiple ways to think about it, but I think about it as going, basically half speed. Okay, so it's going to take twice as long to go through it, because in order to get to this 2 pi, in order to get a full 360 in there, I'm going to have to put a number that's twice as big in for x, because like 720 or 4 pi divided by 2 will finally make the loop for me. Okay, so this is how you slow down a wave. So we just looked at how to speed one up. To slow one down, divide it by something. Right? And so this one, the numbers are easier to do. So if we're going to go half speed, it's going to take us twice as long to make a loop or to make a full cycle. So like here, we started at 0. Okay, we're still going to start at 0. We didn't shift left or right at all. Okay. And then as we go through it, if we're going half speed, if it's going to take us twice as long, well, before we finished at 2 pi, so now we should finish at 4 pi. Yeah, so that's one way of thinking about it. It's going to take twice as long. It's going to take us 4 pi's instead of 2 pi's. Okay, and so just trying to give you a variety of ways to look at this. This is another interesting way to build the table. I know in pre-calc, Mrs. Hartle will use this a lot, where you find the starting point, you find the ending point, and then you kind of paint in the ones in between, because it's all halves. So we start over here, we started at 0, we ended at 2 pi. Well, the middle number is halfway in between those two because it's equally spaced. So pi is halfway between 0 and 2 pi. So what's halfway between 0 and 4 pi? Well, half of 4 pi is 2 pi. Okay, which again takes twice as long to get to. Over here it took until we got to pi, so twice as long as that is 2 pi. Okay. And then it's halves again. So halfway between 0 and pi is a half a pi. So over here, halfway between 0 and 2 pi is just 1 pi. Okay. Halfway between 2 pi and 4 pi is 3 pi. Okay, so you can count out your x's like that if you need to, like that's just a different way to approach it. Otherwise, you notice before we counted in halves, if we're going to go half speed, if it's going to take twice as long, instead of counting by halves, we'll count by whole numbers, which is what we did. We counted by whole pi's. Okay, and then sketching these, so 0, 1 is our starting point, pi 0 is our second point, 2 pi, -1 is our third point, You notice we're already going to go way off the graph. Like the next point is over here, it's 3 pi 0. So it's somewhere off the edge. And then the last point is somewhere way off the edge. Okay, so if you run out of room on the graph, you can always trace this backwards because it's cyclical. So it's going to go down here, it's going to go up, and since it's bouncing back and forth between +1 and -1, the next one is going to be right there, because notice they're going every 4 boxes, so I'm going backwards, every 4 boxes, down to -1. So this is now one incredibly slow wave that we're looking at. Okay, so it's spread out way slower, half speed. Okay, so if you want to slow one down or speed it up, it all happens in there. And those are the horizontal transformations and the end of transformations of trig graphs.